All right, so number 16 is a pretty involved rational function with a lot of different parts. So I'm going to go ahead and write this out right quick because we're going to analyze it for its behavior. Domain, x-intercepts, y-intercepts, vertical asymptotes, holes in the graph, and in behavior model, and your limits. As x approaches negative infinity and as x approaches positive infinity. Okay, so let's first look at this original factored form. What I see is I have an x plus 3 squared and I have an x plus 3 in the denominator as well. So I know that one of those can simplify out. Okay, now normally when something simplifies out, you've got to assess whether or not it's going to be a hole in the graph or a vertical asymptote. The way to check is when you plug in -3, right? So -3 is where this equals 0. If you plug it into the remaining expression, if you get a number, then it's a hole in the graph at that number. If you get undefined, it's a vertical asymptote, okay? So if you cancel two things out, if you cancel two factors out, and then you plug in the root of that binomial, so -3, if you plug it into this expression that's left over and you get a number, be it 0 or like 5, then it's a hole in the graph. But if it's undefined, a number divided by 0, then that's a vertical asymptote, okay? So in this case, I know that when I plug in -3 into what's left over, this right here is going to be -3 plus 3, which is going to be 0, and then -3 minus 1, -4, -6, -7. I'm going to plug it in down here, and I'm going to get numbers. But this is going to be gone, so I'm going to get 0 times a bunch of other stuff, which is 0, divided by a number, right? Which means I know there's going to be a hole in the graph at -3, 0. Okay? So I'll go ahead and graph that, -3, 0. I know there's a hole in the graph. Okay, let's see if anything else cancels out. I've got x minus 1, and yeah, I've got an x minus 1 on the top and an x minus 1 on the bottom. Okay, again, I canceled out this binomial, so I'm going to plug in 1, which is the root of the 0 of this binomial. I'm going to plug in a 1 into what's left over. In fact, I'm going to go ahead and see what's left over. Okay, I'm going to write the expression with everything gone that can be factored out. So don't forget that negative, because that's kind of ruins things if you don't see it. So we were left with 1x plus 3, an x minus 3, a 2x minus 1, an x plus 4, an x minus 2 quantity squared, and that's it in the denominator. Okay? It's a little bit easier to look at this whenever we're plugging in the numbers. So I could have plugged -3 into this, and I got 0 over a number. Okay, so 0. And now I'm going to plug in the root of that, 1. So I'm actually going to do that down here so I can see it. So I've got negative, and when I plug in 1, I've got 1 plus 3, which is 4, 1 minus 3, which is -2, 2 times 1, which is 2 minus 1, is 1, over 1 plus 4 is 5, and 1 minus 2 is -1, and -1 squared is 1. Okay? So what I end up with is -4 times -2, which is +8 over 5. So I know I have a hole in the graph at the 1, 8/5. And I'll go ahead and graph that as well. 1 8/5. So 5 goes in 8, 1 time with 3 left over, so that's 1 3/5 or 1.6, because 3/5 is 6/10. Okay? So around 1.6. 1.6. Okay. All right. Then let's just carry on with domain. So domain is you're just identifying where the function exists, and so the easiest way to figure that out is to just find out where it doesn't exist, especially with these types of functions. So I know that I'm going to go back to the original, because if I only use this, then I'm going to miss out on something. Okay. What you miss out on are holes in the graph, and it's like, well, no, we don't exist there. They're discontinuities, right? So I go back to the original, and I know the original doesn't exist at -4. It doesn't exist at 2. It doesn't exist at -3, and it doesn't exist at 1. Okay, so my domain is everything but those numbers. Let's go ahead and address the other two in the denominator, though. So we've already talked about -3 and 1. Those are holes. Yeah? So what are -4 and 2? Well, if it's only 0 in the denominator, then it's got to be a vertical asymptote. So I know I have a vertical asymptote at x equals -4 and at x equals 2. Okay, and I'm going to go ahead and sketch those. X equals -4 and x equals 2. Now let's talk about these vertical asymptotes because they're a little bit different. X plus 4 has a multiplicity of 1, and having a multiplicity of 1 means, so quick little thing, if I have a vertical asymptote and the multiplicity is odd, yeah, that means at the vertical asymptote, the function is, if it goes down on this side, it has to go up on this side, okay, or come from infinity. But if it, and vice versa, if it goes up on this side, then it's got to be coming from negative infinity on that side, okay? But if your multiplicity is even, then that means when you approach the vertical asymptote, like so from this side, say it's going up, then that means it has to leave from up there, okay? And if they're both going down, then this has to be coming from there as well, okay? So that's the difference. Now, if you're an x-intercept, an odd multiplicity means you go through it, an even multiplicity means you bounce. But when it comes to vertical asymptotes, that means whether or not you change signs. If we change sign here, we stay the same sign here, okay? So in this case, here we're going to change because there's a multiplicity of 1. And here we're going to stay the same because at 2 we have a multiplicity of 2. Okay? And we'll come back to that later whenever we see them. Okay, now let's talk about x-intercepts. So x-intercepts occur when only the numerator equals 0. So the numerator equals 0 at, well, I would say -3, but I already know that's a hole in the graph. Okay, so I mean it is an x-intercept, but it's just not, it doesn't exist there. We also have +3. So +3 is an x-intercept. I'm going to go ahead and put it out there. And also 2x minus 1 equals 0 at 1/2, so also 1/2 is a 0. Okay. Y-intercept. Y-intercept occurs when x equals 0. So when x equals 0, you could use this right here and figure it out. Or you could use the original expression. Okay, so I'm going to show you that it works with both. If x equals 0, all of these terms are gone on the top, right, with having x in them, except for this right here, 27 over -48. So in fact it is, well, 27 divided by -48, float the negative to the top, but they both divide by 3, right? 48 is 12 times 4, which is 3 times 4 times 4, so it's 3 times 16. So if I divide this by 3, I get -9/16. So, I mean, it's a little over half. So I know that the y-intercept is a little over halfway down. It's a little over -1/2. Okay. So somewhere in there, right? I'm also going to show you that I can get it from here. So if I were to plug in 0 into this, I've got -0 plus 3 is 3. 0 minus 3 is -3. And 2 times 0 is 0, minus 1 is -1. Over 0 plus 4 is 4. And 0 minus 2 is -2, but -2 squared is, well, I'll just go ahead and write that, +4. So you see how we get negative times a negative times a negative is a negative. 3 times 3 times 1 is 9. 9 over 4 times 4 is 16. So you can get it in multiple ways. You can just plug it into what's left over, or you can go to the original expression. Okay? Either way, that is -9/16. Okay. In behavior model, so let's talk about powers. The original function is, well, on the top. So if you look at the original, the numerator has the highest degree is 5, and the denominator the highest degree is 5. And if they grow at the same rate, which is a power of x of it, then the in-behavior model is really just the ratio of the leading coefficients. So we actually have a horizontal asymptote at y equals -2, which means my limits as I approach the infinities are -2. Okay, so that's a horizontal asymptote at -2. I'm going to go ahead and sketch that. Okay. So now it's time to sketch. All right. So the thing about this graph is that I've got a lot of clues in the interior. I've got a lot of things about this that tell me that I'm probably going to do something like this. And I've got this x-intercept here, which tells me I'm probably going to be up here and doing this. And I've got no x-intercept, which means I'm probably going to be doing this. And guys, honestly, if that's what you use to identify, I mean, you're probably right. And that's, I'm not going to be looking for any specific points other than these right here, okay? If you wanted to check and make sure, you could plug in a specific point. I'm quite positive that this is up here and approaching the horizontal. I'm not going to have one on the test where you have to dip down below, okay? It's not going to do that. And even if it did, I wouldn't expect you to find that, all right? So it wouldn't count off. So just using purely deductive reasoning. I don't have an x-intercept, so I think I'm going to do this. Okay, quick thing right quick. If I don't have an x-intercept here, and my horizontal asymptote is 0, then there's no indication whether or not you're above or below, in which case you can do a sign chart and say, okay, plug in an x value over here into your factor form, your simplified, and just see whether or not you get a positive or a negative, and that would tell you whether or not you're above or below, okay? But in this case, I'm quite sure I'm below, so I'm going to tilt the paper so I can draw. Now, I am going to be picky. I do want it to look like you're approaching the asymptotes, okay? So sometimes people are getting kind of like lazy about it. You just kind of draw down. Like, that doesn't work, okay? I need to see that you're actually approaching the asymptotes, the horizontal and the vertical, okay? All right, so like I said, when we talked about the vertical asymptotes, we talked about changing sign and staying the same. At -4, the multiplicity is 1, which means it's odd. So if I'm down here on this side, then I have to be up here on this side. So I know I have to come from up here, right? So none of these x-intercepts, either the 1/2 or the 3, have a multiplicity of 2. It did have a multiplicity of 2, but then we cancel 1 out, making it a hole in the graph. So I know I have to cross here. So better do look at this. It's a multiplicity of 1. I have to cross, and then I have to cross, and I have to cross, right? So all of these have to just cross. You can't bounce, so that means I have to come from here, bounce, cross through. I have to go through this y-intercept. I have to cross through, go through that, which leads me to believe that I just go straight up there. So that's what we're going to do. So I'm going to come down here, go through that point. I don't know how low I go, but that's fine, whatever. I go through this point, through that point. Please don't go through the hole. Approach it and then leave it. And then go up, right? Then also remember, this vertical asymptote at 2 had a multiplicity of 2, which means if I'm up here on this side, I have to be up here on this side. Okay, that's the equivalent of the bounce. So we go through here. I know I need to cross through there, cross through my x-intercept, and then I have to approach the horizontal asymptote, and there we go. And there's your graph. Okay, so now we're going to use the graph to answer these limit questions. Zoom out a little bit. Okay, so the first question is the limit as x approaches infinity. So we actually already answered that. The limit as you approach infinity is -2, but just looking at it, that's saying, hey, as x goes to infinity, what's the y value going to? And as x approaches infinity, the function is going to -2. -4 from the left. So if I approach -4 from the left-hand side, then it looks like it's going down, so that's -infinity. Okay? -4 in general. So if there's not a plus or a minus sign, that means approach it from both sides. So if I approach -4 from both sides, on one side I'm going down to -infinity, on the other side I'm going up to positive infinity, which means they don't approach the same thing. So this one does not exist. All right, -3. So -3 is just an x value. So if I go to -3, the function on both sides is approaching the y value at -3, and the y value at -3 is 0. +3. So +3, 1, 2, 3. At 3, we are again approaching the x-axis. So in that case, it's also 0. 2 is the vertical asymptote. Okay, so this one's interesting. It doesn't have a left or a right, which means both sides. So if I approach it from both sides, you actually have two different answers you could say. You could say it does not exist, but a more apt description is that both sides are going up to positive infinity. But it would be acceptable for you to say it does not exist on that as well. Okay, 0. So if we approach 0, well, 0 is my y-intercept, so I go to the y-intercept, and we are approaching negative 9/16. A negative infinity. We already answered that. Limit as you approach negative infinity is negative 2. As x goes to the left, the function is going to negative 2, the y value. Negative 4 from the right-hand side. So if I'm approaching negative 4 from the right-hand side, that means I'm going up to, and you don't have to like come from over here and like say, okay, well, I'm doing all this junk. No, literally go to negative 4, go a little bit to the right, and then approach it. Going up to positive. All right, 1/2. So if we're approaching 1/2, 1/2 is an x-intercept, so as x approaches 1/2, the function on both sides is approaching 0. 2 from the right, so 2 from the right-hand side, so I'm going to approach it from the right, going up to infinity. And 1. So 1 is a hole in the graph, so both sides, doesn't matter there's a hole in the graph, it's just a y value, right? So the function on both sides is approaching that moment 8/5. So that limit would be 8/5. And there's that function. Okay. Number 17, I asked you to find all these limits, just looking at the graph, so let's talk them out. Okay. I just want to look right quick about what's going on. X minus 1 cancels out, which means that's the hole in the graph at 1. Anything else cancel out? No? Okay. So let's just look at it. Limit as you approach negative 2 from the left. So here's negative 2. I'm approaching it from the left-hand side. That looks like it's going up to infinity. So I'm going to go ahead and give that my answer. Negative 8. So if I approach negative 8, it looks like negative 8 is an x-intercept because it's 0 on the top and not anywhere else. So that, I'm going to say, is 0. Limit as you approach 2. So 2, it looks like it's an x-intercept, and if I look up here, in fact it is, and that multiplicity of 2 is why it bounced, right? So that's an x-intercept, that means it's 0. 3 from the right. So 3 looks like it's a vertical asymptote. So if I approach it from the right, it looks like it's going up to infinity. All right, 1 from the right. So 1 looks like a hole in the graph, and it is. So as far as like what it's approaching, it looks like it's approaching negative 1, but I'm going to have to plug it in to find out for sure. So let's plug in 1. 2 x equals 1. 2 times 1 plus 4 is 5. 1 minus 2 is negative 1, and negative 1, negative 1 squared, which is just positive 1. 1 plus 8 is 9, and 1 plus 1 is 2, divided by. 1 plus 2 is 3, so 3 to the 4th, and 1 minus 3 is negative 2. Okay. I'm going to simplify before I multiply. Okay, makes it a lot easier. I noticed that 2 and 2 can cancel out, leaving me with just a negative 1 down here. 9 is 3 squared, so 3 squared can cancel out with 2 of those, leaving me with just 3 squared in the denominator. So here's what I've got left. 2 times 5 times 1 times 1 times 1, so that's 10. Over 3 squared is 9 divided by negative 1, so that's negative 9, so negative 10 nines. Okay? So it's close to negative 1, but it's not quite there. Or it's past it. So that is negative 10 nines. Okay, 3 from the left. So 3, again, is the vertical asymptote, or one of them. So 3 from the left, you're going down to negative infinity. Okay. Negative infinity, as we approach negative infinity. So as the function goes towards the left, the function, it looks like it's getting closer and closer to the horizontal asymptote 2. And if I look at the powers, I've got 1, 2, 3, 4, 5, 6 on top. 1 plus 4 is 5, plus 1 is 6. So they have the same degree on top and bottom, which means it's 2 over 1. So that would be horizontal asymptote 2, which you don't have to go through that because you can just see it right there on the graph, okay? Limit as you approach -2. So -2 is vertical asymptote. So normally vertical asymptote, you think, oh, almost for sure it doesn't exist because they go to opposite sides, but in fact they both go up. And that makes sense because this right here has an even multiplicity, so it means they're both going up. So I can say positive. Okay. It says true or false. If false, correct limit. Limit as you approach 3 does not exist. So 1, 2, 3. Yeah, left hand side goes down, right hand side goes up, so that is true. All right. Limit as you approach infinity is 0. So limit as you approach infinity, so as x goes to the right, the function looks like it's approaching the horizontal asymptote, so that's false, and that should be 2. And limit as you approach -1 is infinity. So limit as you approach -1. Well, it looks like when you approach -1, that's an x-intercept. So it's not that it's going to infinity, it's going to 0. Okay? All right, let's talk about 18. So on 18, I've got to write a function that fits these characteristics. So the first thing I'm going to do is draw a fraction line and go ahead and start putting things where I know they need to go. I need a vertical asymptote at 2, which means I need an x minus 2 in the denominator and not on the top. Okay. I need a hole in the graph at -4. That means a factor on the top and the bottom. So x plus 4 on the top and x plus 4 on the bottom. You can come in! Oh, no, you can't. Sorry, I'm making a video. You can use calculator. Okay, and then I need a horizontal asymptote at -1. So that is interesting because it implies that you need to have the same power on the top and the bottom, and the ratio needs to be -1. So let's look at this last part before we figure that out. I need a positive x-intercept. So the only reason I said let's look at this last part is because that kind of helps us answer that. A positive x-intercept means in the top I need to have a factor. That would indicate that I have an x-intercept that's a positive number. So it definitely can't be 2 because that's vertical asymptote. So literally x minus anything, 7, right? Now that means I have a power of 2 on the top and the power of 2 on the bottom, which is good. That means I have the same ratio. But now I need a horizontal asymptote at -1, and right now it's a positive 1. So for that, I'm just going to put a negative on the top. You can put it on the bottom, but there you go. And now I have satisfied all the conditions. Okay, number 19. We need a vertical asymptote at -3, which means I'm going to go ahead and put x plus 3 in the denominator. And not the numerator because it's a vertical asymptote. Although if I need it, I can put it on the top and bottom as long as I have more of them in the denominator. Oh, and at x equals 5. So I need another one, x minus 5. I need a hole in the graph at 2, 0. Interesting. Okay, that's actually 2 different things going on at once. I need a hole in the graph, which means I need the factor on the top and the bottom. So I need an x minus 2 and an x minus 2 on top. But it says it needs to be a hole at specifically 2, 0, which means it's at the x-axis. So that means you need more of the factors on the top than on the bottom. Okay? So that means if I were to plug in, if I were to cancel one of these out, I'd still be left with one in the numerator. At least one in the numerator means that when I plug in 2, I would get 0 divided by a number. Okay? So a hole at the x-intercept, or at the x-axis, means there's more factors on the top than the bottom. Okay, so last thing. I'm supposed to have a slant asymptote. A slant asymptote infers that Specifically, you have a higher power on the top by 1. Right now, the degree in the denominator is 1, 2, 3, and the degree in the top is 2. I need the degree in the top to be 1 more than the numerator, which means I need 2 more. So you could do this a lot of different ways. You could just put an x squared in the front. Okay, that would be one way to do it. You could put x plus, well, literally anything but those, x plus 5 and x plus 10. That would give me a degree of 4 on the top. Anything except the factors in the denominator, as long as you have 2 degrees more, then you're good. I'm going to go ahead and just stick with the x squared because it makes it easy. People won't wonder where I'm getting these other numbers from. And there you go. Degree is 4. Degree is 3. If the degree on the top is greater by 1, then you have a slant asymptote. Okay. Now number 20. Okay. I need a vertical asymptote at 4. So x minus 4 in the denominator, not in the top, with the same sign on either side, which means I need to have an even multiplicity, so I'm just going to go ahead and say 2. That takes care of that. And at x equals 0, with the signs changing on either side. So a vertical asymptote at 0 means x minus 0, or just x. And it says with the signs changing, which means I need to have an odd multiplicity, so I can just leave it as 1. I need to have a hole in the graph at -3. So that means I need to have an x plus 3 on the top and an x plus 3 in the bottom. I need an x-intercept at 2, which means I need an x minus 2 on top and not the denominator. Oh, with the same sign on the other side, so I have to bounce there, so I'm going to at least do a power of 2. And I need a horizontal asymptote at 0. Now, horizontal asymptote at 0 means I have a greater degree in the denominator than in the numerator. Right now the degree is, in the numerator is 3, 2 plus 1, and the denominator is 1, 2, 3, 4. So the degree in the denominator is already larger than the degree in the numerator, so that is already satisfied. We're good. Okay, now if you had picked like, you know, this x minus 2, the x-intercept with the same sign on the other side of the bounce, if you'd picked a higher degree, like say 6, because it's even, then you would need to make this something more. Okay, you'd have to add on something to make it have a higher degree. Okay. 21. The variable x varies directly with y. So what we first want to do is write the expression and then go from there. X varies directly, so direct variation means multiplication, so I've got some constant of variation times y. If y is 3 when x is 10, so 10 equals k times 3, and what is y when x equals 22? Okay, so if I solve this for k, the constant of variation, I get 10/3. So I'm going to write this equation now with 10/3. X equals 10/3 y. Okay, that's what you're always going to do. You use the first set of data to find the constant of variation, and then you have the equation relating variables. What is y when x is 22? So when x is 22, let's solve for y. So I want to get rid of 10/3, the opposite of, so I could divide both sides by 10/3, but it makes better sense to just multiply by the reciprocal. So I'm going to multiply by 3/10. And 22 divided by 10, they're both even, so 11/5. So I'm thinking 33/5 is y. Okay. 22. The variable c varies directly, so it means multiplication, so k times the sum of w and 3, so w plus 3, and indirectly with the square root of g, and indirectly, which means division, the square root of g. Solve the equation for w in terms of c and g, so I need to solve for w. So, okay, looking at this equation, I need to get everything away from w. I need to get rid of the plus 3, the times k, and the divided by square root of g. Pretty sure it's still recording, but my computer just... Okay. So, the opposite of division is multiplication, so we're going to multiply by the square root of g. I need to get rid of that k. I could distribute it and work it that way, but I'm just going to go ahead and divide it. So c times the square root of g divided by k equals w plus 3. And the opposite of addition is subtraction, so I'm going to subtract. C times the square root of g divided by k minus 3 equals w. Okay. If w is 13 when c equals 2 and g equals 16, so let's take care of that first. I'm going to go up here. W equals c times the square root of g over k minus 3. If w is 13 when c equals 2, g equals 16, so that means it's giving me information to solve for k. I've got 13 equals 2 times 4, so 2 times 4 is 8 divided by k. K equals, so divide by 13, I got 8 13s. I'm going to multiply by k, that's what I did, and then I divided by 13. So I get k equals 8 13ths, and that means w equals c divided by, or c times the square root of g divided by. So it's kind of weird to say divided by 8 13ths, so we're actually going to multiply by 13 eighths. So 13c square roots of g over 8 minus 3 equals w. Then what is c when, then what is w when c equals 6 and g equals 81? So what is w when c equals 6 and g equals 81? So square root of 81 divided by 8 minus 3. So square root of 81 is 9. That's not how I intended the numbers to work out, I don't think. Sorry, I'm thinking for a second. Yeah, we got that okay? So just oh, I forgot my, well, that's rude. I knew something was wrong. I'm just kidding, guys. Sorry about taking you down that rabbit hole. You probably caught it before I did. I forgot the minus 3. It's kind of annoying. I did not remember making that problem that weird. Okay, so minus 3. Means a whole lot. Okay, so now we're going to solve for k. The first thing you want to do is add the 3. So you get 16 equals 2 times 4 divided by k. 16 equals 8 divided by k, multiplied by k divided by 16, k equals 1/2. That's a little bit better. Okay. So now we're going to go back to the original expression. W equals c times the square root of g divided by 1/2. Dividing by 1/2 simply is multiplying by 2. So I'm just going to say 2c square roots of g minus 3. Okay, so now it says what is w when c is 6, g is 81. Okay, so I've got 2 times 6 times 9 minus 3. 2, so 12 times 9 minus 3. 12 times 9 is 90 plus 18, so 108. 108 minus 3 is 105. Okay. Sorry about that. All right, let's talk about 23. So So 23 has multiple parts, so we'll go ahead and start with the beginning. The variable w varies jointly with x and the square of y. So joint variation means multiplication at least twice. So w, constant variation, times x and times y squared, and inversely with 2 less than z, which means divided by z minus 2, 2 less than z. Okay? If w equals 4 when x equals 9, y equals 2, and z equals 8, so, okay, so that means we want to solve for k using the first part and then solve for w using, once we know k. So if w equals 4, when x equals 9, y equals 2, and z equals 8. Okay, so let's solve for k using that. This is 6, this is 4. 9 and 6 can simplify, or you can think 36 divided by 6 is 6, so I've got 4 equals k times 6. So that means k equals 2/3 divided by 6. Yeah, okay. So that means, going back to this equation, that actually means w equals 2/3. So a lot of people would write like 2/3 divide, and all that. I'm going to go ahead and put, deal with the fraction as it is. If w is 2/3, that means 2 and a 3 on bottom. Sorry, if k equals 2/3. There you go. So times x times y squared times z minus 2. Okay, so I'm going to use this equation. What will w be when x is 15? So 2 times 15 times 3 squared, which is 9. I'm using this equation right here. Over 3 times 11 minus 2, because z is 11. So 11 minus 2 is 9, and so those would just cancel out. 15 divided by 3 is 5, so it would be 10. So first here, then here, here, and then here, and then we went there, which led us to our answer. Another color. Is it terrible? Okay. All right. Now, part C implies that we're going to go back to the beginning. It says solve the equation in A for y in terms of w, x, and z. Back to general K. So, okay. W equals k x y squared divided by z minus 2. I need to solve for y. So the opposite of division is multiplication, so we're going to go ahead and multiply by z minus 2. W times z minus 2 equals kx y squared. I need to solve for y, so I'm going to divide by kx. W times z minus 2 divided by kx equals y squared. And then we've got to take the square root. Y equals plus and minus the square root of w times z minus 2 divided by kx. Okay. And then it says, if y equals 5, so we're going back to this original one. If y equals 5, so that means it's a positive square root because it equals a positive 5. When x equals 5, w equals 7, and z equals 14. Then what will y be when x equals 1, y equals 20, and all that? Okay, this does not look like it's going to be a perfect answer, so I've got 5 equals the square root of 7 times 12. So that's 70 plus 14, so 84 divided by 5k. So we need to solve for k. So the opposite of the square root is the square. So I've got 25 equals 84 divided by 5k. I did not, like, I picked random numbers because I specifically wanted this one to be just weird. And you can use decimals. You could just solve this using your calculator. So we're going to multiply by 5k. So 5k times 25 is 125k equals 84. K equals 84 over 125. So if you do have a calculator in these, instead of using 84 over 125, you could just say what 84 over 125 is. So 0.672. Okay? So that means, go back to the equation. It says y equals plus and minus the square root of w times z minus 2 divided by, sorry, I'm going back to this one, k, which is 0.672 times x. And so then the last part, it was, what will y be when x equals 1? So 0.672 times 1. Y equals 20. Oh, that's not supposed to be y, that's supposed to be w. W equals 20, and z equals 8. Okay, so this is not going to be pretty, so I'm just going to type it in. Square root of, well, let's do this so you can see it. 20 times 6 divided by 0.672. And that is either positive or negative 13.363. And there you go.